Good day, dear participants. Today I'm going to present you my work, an approach to assessing the reliability of software systems based on a graph model of the method dependence. Nowadays, software has become an integral part of our lives. Almost all programs we deal with make our lives easier, providing us with the comfort that people of the previous generation could not even dream of. In order to meet the growing demand for the software, the IT market all around the world, and in Ukraine in particular, also growing and changing rapidly. And it could be seen from this graph that in last 10 years, market in Ukraine was grown almost 3 times. In addition to the obvious market volume expansion, there are also internal changes in industry driven by a desire to increase software development speed and reduce the final price. Since the high quality is an important component of its success, quality assurance and control are tasks that must be addressed at the early development stage. According to ISO 25010-2011, software quality is determined by 8 metrics, which you could see on the screen here. In this work, we considered reliability only because it's the only one of those which couldn't be assured by proper software architecture at the development stage. Right now, the 3 categories of reliability assessment models are present for the software reliability assessment. The first one is the most old one, the black box analysis. It's the most inaccurate one because these type of methods, they don't take into consideration everything which is under the hood of their application. They based only by the consequences of its operation. The next type is metric-based analysis. It's a sort of step forward, but at the same time, these methods, they take into consideration metrics like amount of code lines or amount of methods, so they are still not very accurate, but at the same time, as I mentioned, it's a step forward. And the final category is the architecture-based analysis methods or white box methods. This type of methods, in terms of being done properly, could provide the best results comparing to the previous 2 categories. According to the approach we suggested, we are going to represent the application as a graph where all the methods as a graph vertices, and the edges of this graph are probabilities of transitions between the methods. As you can see here, there are 5 vertices here, so it means that the application which is shown here contains 4 methods because we need 2 extra vertices in order to make the calculation and in order to have entry and exit points here. The values P0, P1, P2, and then it's the probabilities of fail-free operation for the methods, and the values P1 to 2, 1 to 3, 1 to 4 is the probability of methods 2, 3, and 4 being invocated, respectively being invocated from the body of method 1. On the next stage, we are going to create matrix by the dimension of M, where the M is amount of methods in application plus 2 extra vertices which are on a graph, and calculate the values as it's shown here. The next step is using the metrics which are calculated in the previous step. They calculate the final metrics T, which are going to use to calculate the fail-free operation probability. The first formula is for the graph which doesn't have loops, and the second one for the one which does. In terms of source code, in terms of graph, the loops appeared in the application which in a source code has recursive method invocations. Here on the flow chart, you could see our implementation of suggested approach. On the first step, we have to do the source code analysis. We have to do that in order to find out which methods we have in application and set the list of exceptions, maybe which, for example, which methods we are going to skip during the processing. On the next stage, we are setting breakpoints for all methods that we are going to process. Breakpoints needed in order to main thread stopped during the execution, then method invocation was recorded, and then the main thread was resumed and program execution is continued. On the next stage, we are going to literally execute the program. So once everything is done and we are going to testing, we run the program on a debug mode and do the testing. After the testing is done, on the next stage, we are going to deal with the information which is collected. The first step is the parsing log file. We need to do that in order to find out all the exceptions which were thrown during program operation and align them or assign them to the to the methods. And we have to calculate all the methods invocations in and calculate probability of fail-free operation for each method, and transition probabilities based on the information that we got from the log file and which were recorded during breakpoint reached. And then, having this information, we could build a graph of our software system and then calculate fail-free operation probability. Here, you could see the comparison of two applications being tested by this proposed approach. The first application, which host code is provided on a paper, is quite simple application. It's just simple loop, which just make math calculation. The second one is the more complicated, as it could be seen from this table. It has 11 methods inside, and it's web-based screen framework application which deal with database and which save some files to the file system. So it's a bit more complicated application. It has more than one entry point, so that's why it couldn't be assessed by general calculations. Next row on the table is execution time in the latent environment. This time represents how much time needed for application to be executed without any stopping, without any breakpoints and stuff like that on a clear environment. And the second line is the time that needed for application to be executed during our investigation. So as it could be seen from the table, for the first application, the difference between time in an insulated environment and in debug mode is quite significant. It could be explained by the fact that the first application is depends only on CPU time. So once we stop the thread and do some extra operation, it's obviously slow down the application execution. So that's why the difference is really significant. At the same time, for the second application, which has quite slow operation like database recording, file system recording, this difference is unnecessary because the CPU is not the weak point of the second application. This next line on this table is log file size. For the first application, log file size quite big because it's just a loop which iterates through the all integer values, so it produces a lot of exceptions during that. And that's why log file contains a lot of information. But for the second application, log file is quite small, as it's quite usual for such application. On the next line, we could see how much time we need to process the log and find and select and release all the information about exception from it. From the first application, it took 36 seconds. For the second application, it takes 27 milliseconds. Here I have to highlight that 46 seconds for the first application. It works so fast because it was done on a quite high-speed SSD drive. So for HDD drive, it might take a while. The second line shows us the amount of time needed to matrix calculation, and this could be seen from there. The second application more than twice bigger than the first one, but at the same time, it doesn't need a lot of time to be calculated. And the final row is fail-free probability, operation probability for the first application. 93%, for the second application, 97%. For the first application, the comparison tests were done, and we calculated the fail-free operation probability by traditional methods, and by these methods, the value was exactly the same. As a conclusion, I could say that the approach was implemented as a plugin for integrated development environment, IntelliJ IDEA, and this implementation could measure reliability of the programs written in Java. With minor changes, it could be adapted to work with any object-oriented programming language. The objective was to develop an approach that would make it possible to evaluate the reliability of both the entire software system and specific modules on the testing stage. As it was mentioned before, this application could select some list of methods that we could like to assess. So it means that we could make an assessment for the part of application. Upon testing completion, reliability indicator is calculated, which could be used to make decision about the feasibility of further program improvement. Yeah, that's it on my side. Thank you for attention.